Mammals are astonishing in their variety. From the skies to the seas, grazers, hunters, cooperators, energetic and not so energetic, climbers, burrowers, big, indeed biggest, and small, one of the most diverse groups of animals on the earth, and yet all are connected to each other. "28 orders, 153 families, 1,200 genera, in total some 5,500 species, including ourselves. All united in a single class representing our origin from one common ancestor. And even that ancestor was only the most recent in a long lineage stretching back into the depths of time on a scale so large as to be incomprehensible to the human mind. This is the story of our ancestors and their multi-million-year journey. There are lots of familiar faces among the mammals. As mammals ourselves, this is probably the animal group with which we are most familiar, scientifically and intuitively. It's easy for us to see elements of ourselves in other mammals, especially our closest relatives. Many of the characteristics that we find pleasing in other organisms, like big eyes, fuzziness, motherly care, and playfulness, come from a mammalian bias. This inherent familiarity is a product of the close evolutionary relationship we as humans have to all other mammals. The biological similarities we share amongst ourselves are also the reason mammals are one of the most scientifically well understood groups of organisms. Living mammals fall into 6 major groupings: the monotremes, the marsupials, and the placentals, which contain 4 major groups: Xenarthra, Afrotheria, Laurasiatheria, and Euarchontoglires. We'll discover the basis of these groupings later. But what about the group Mammalia itself? What exactly is a mammal in the first place? When you think about what makes mammals unique, some characters will probably come to mind very quickly. Characters like mammary glands, warm-bloodedness, giving birth to live young, and hair. But monotremes like the platypus are also mammals, and they don't have mammary glands, not with nipples like all the other mammals anyway, and they also lay eggs. What about fossils? How can we tell from bones whether or not an animal had fur or metabolically controlled its body temperature? Of all the characters we associate with living mammals today, which of them are actually necessary to be called a mammal? Taxonomy, or the classification of living organisms, is a very complicated field, and determining how to define taxonomic membership is an ongoing process. A long history of comparative studies on hundreds of fossil specimens and living mammal species suggests that the key defining feature of Mammalia is in fact in the skull. If you're a member of class Mammalia, you almost certainly have a middle ear composed of 3 small bones or ossicles, the malleus, incus, and stapes. For the more curious, though, this is likely unsatisfactory. Why this particular character? Why choose to draw the line between mammal and non-mammal here? As humans, we like to categorize things. It makes our lives easier and is vital for allowing us to model and understand our surrounding universe. Of course, some categories are more meaningful than others, and where taxonomy is concerned, biologists strive to make sure that taxonomic categories are directly based on evolutionary history. Think for a moment about your own evolutionary history. You are the same species as your parents. Likewise, your children, if you choose or have chosen to have any, are the same species as you. This is intuitively obvious, but remember that all of your ancestors, going back to the very first forms of life on Earth, can also make this claim. If we were to follow our evolutionary lineage in a strictly cladistic fashion, somewhere in our ancestry there was an individual animal that sired both a mammalian and a non-mammalian offspring. Yet both were of the same species. Conceptually, this at first seems like a paradox, and lies at the heart of much misunderstanding about evolution. A key point that I feel is consistently brushed over when evolution is taught, in high school especially, is that taxonomic groupings are lineages. Species, families, classes, these are all intrinsically historical entities. Cladistically, yes, one of these is a mammal, and the other isn't. But that difference is only evident in hindsight. For the sake of practicality, we associate certain lineages, like mammals, with specific characters, such as a middle ear apparatus consisting of 3 bones. But these defining characters are just artifacts of a temporal process. A species is a lineage, not simply a collection of living organisms or a set of characters. If we had a very powerful time machine, we could track the ancestry of every organism on the Earth and physically draw the tree of life as one giant pedigree. And with that level of knowledge, perhaps we wouldn't need taxonomic categories. But we don't have a time machine, so all we have are the organisms around us, and fossils of course, to observe and give us clues. Taxonomy and the reconstruction of phylogeny are really just sophisticated tools for approximating evolutionary history, and by using characters to aid our classification schemes, we can infer common ancestry in a collection of organisms. Essentially, it's this working backwards approach, which we have no choice but to use, that can often lead to the misunderstanding that we are in fact defining evolutionary lineages by their features, not simply using features to hypothesize lineage. This may seem like just a difference of semantics at first, but it's actually very important, and becomes obvious when you make an analogy to archaeology, for example. Thus, at a lineage's inception, especially if that lineage is old, the organisms often don't resemble all or indeed most of their descendants. Unfortunately, though, many taxonomic names are descriptive, which just helps the confusion. So the word mammal essentially means that we recognize all organisms with 3 middle ear ossicles as having a single common ancestor that makes them all more closely related to each other than to all other animals. The importance of these ear bones, which at this point may seem trivial, will become clear as we journey back in time and become more familiar with some of the earliest mammals and their closest non-mammalian relatives. First, we acknowledge that mammals are vertebrates, and share this membership with all other animals that have a backbone and spinal column. Mammals are also tetrapods, which include all vertebrates that have a 4-limbed ancestral condition, and with this junction we diverge from most of the fishes, the jawless fish, cartilaginous fish, ray-finned fish, and the lobe-finned fish. Mammals are also amniotes, which are tetrapods that have a terrestrially adapted egg. This egg has several specialized tissue layers that prevent it from drying out of the water and protect and nourish the embryo through a long developmental period. The newborn resembles the adult, and there's no larval stage, so it's at this junction that we diverge from amphibians. In geological time, this has brought us from the Cambrian period through most of the Paleozoic era to the late Carboniferous period, just over 300 million years ago. Amphibians were the dominant vertebrates for much of this time in a warm, humid, and highly oxygenated climate that they shared with a diverse array of large arthropods. The Earth's climate is in a cooling, drying trend, a change driven by the southern movement of supercontinent Gondwana and its subsequent glaciations. This trend devastated many of the tropical biomes, resulting in the deposition of coal forests in a geological event known as the Carboniferous rainforest collapse. This cooling, drying trend was likely a major selective pressure contributing to the evolution of amniotes, which split into two major lineages at the end of the Carboniferous. These were the early Synapsids, the ancestors of all extant reptiles, birds, and dinosaurs, and the early Synapsids, the ancestors of mammals. Synapsids experienced a large radiation after the Carboniferous rainforest collapse, expanding into the drier climates less accessible to amphibians and arthropods. But until the onset of the Mesozoic era, they were not the dominant vertebrates in their ecosystems. In the late Carboniferous, that distinction belonged to a group of synapsids called the pelycosaurs. Synapsids are distinguished from other amniotes by an opening in the temporal region of the skull behind the eye. This is a modification related to adaptations in jaw musculature that improve bite force. Pelycosaurs were a successful group that occupied a wide variety of ecological niches and included both carnivores, like the famous Dimetrodon, and herbivores, like the Casids. These animals would have been rather reptile-like to look at. Like the other amniotes of the time, they laid eggs, and were unable to metabolically maintain stable body temperatures. They did not have hair, but instead had osteoderms and horny scutes. These are bony dermal structures that resemble lizard scales, but which are different anatomically. Crocodilians and birds, in fact, have dermal scutes, as do some living mammals like rodents and armadillos. Like many living sauropsid reptiles, they also had a separate skull roof that lay over top the upper jaw and inner brain case, attached to them mostly through musculature. This configuration reflects the ancestral fish skull, where jaws are derived from the first gill arch, and where the jaws are anchored to the skull by the hyomandibular, derived from the second gill arch. The slit between these two arches is present as the vestigial spiracle in many sharks, and is homologous with the middle ear cavity in amphibians and amniotes. In amphibians and sauropsids, the hyomandibular is termed the columella, and in multiple lineages, including all living amphibians, birds, and reptiles, it evolved into a single ossicle middle ear structure with an external eardrum. Restructuring of the jaw in these lineages made its function as a supporting element redundant and facilitated its co-option into the hearing apparatus. During the time of the synapsid pelycosaurs, however, the hyomandibular was still a jaw support structure. In the synapsid lineage, this bone is termed the stapes, and because of its functioning in the jaw, it wasn't involved in hearing like it is in living mammals. So pelycosaurs probably weren't very good at hearing, but some lineages may have developed external tympanic structures to provide some measure of sound perception, a rudimentary approximation of the external eardrum that we can see in living amphibians. Though mammalian evolution began, as it did with all organisms, at the first forms of life on Earth, their unique divergence started with the synapsids. In the next episode, we'll focus on a special group of synapsids, a lineage that experienced a most profound evolutionary transition.